So let us begin our discussion of transient analysis of second order circuits by looking at parallel RLC circuits. We're going to look at two types of transient analysis. The natural response, where we're going to look at, for instance, the voltage that's created across parallel branches by the release in energy stored in capacitor, inductor or both. So the capacitor will have an initial voltage, the inductor may have an initial current, and then we look for branch currents that can be found via current voltage relationships. Later on we'll look at the transient analysis called step response, and this is where we find V again across these parallel branches, but the V is generated by a sudden application of a DC source. In this case, because it's a parallel RLC circuit, we're going to put a DC current source into the circuit. Now, energy may or may not be stored when the current source is applied for the step response. Now, as I said, we'll leave that a little bit later. First up, we're going to focus just on the natural response. So to find the natural response for our parallel RLC circuit, we first need to derive the second order differential equation that V, the voltage, must satisfy. Now, we know it's a second order differential equation because there are two energy storage elements in this circuit. Using Kirchhoff's current law, we're going to sum the currents away from the top node, and the sum of those has to be equal to 0. We're going to re-express each of these currents as a function of V by using Ohm's law and also by using the relationship between the current and the voltage in a capacitor through an integral. We can further eliminate the integral, because, I mean really, who likes integrals, by differentiating with respect to t. And when that happens, we can see clearly that we end up with a second order derivative as part of this expression. We can manipulate the equation a little bit further by dividing through by c, arranging the derivatives in descending order, just for clarity, and we end up with a homogeneous second order differential equation. This differential equation has constant coefficients because R, C and L are all fixed values. It's a homogeneous equation because the right-hand side equals 0. Now that's a particular characteristic of the natural response, where there is no source present. Now, we don't need to solve that second order differential equation directly. It's been done thousands of times before, so who cares? We have the general form of the solution, and it looks something like this. This is called the natural response of the circuit. When we look ahead at the step response, there'll be an additional term in this equation, a constant term, which will form part of the step response. Now, looking at this equation in a little more detail, it has four unknowns in here. S1, S2, and these two constants A1 and A2. So what are S1 and S2? They are determined by the circuit parameters R, L and C. They're also known as the roots of the characteristic equation of the circuit. And these roots, as you can see from this equation, influence the behaviour of V of t. Hence it's called characteristic. The constants A1 and A2 are determined by the initial conditions of the circuit. In this case, what's going on in terms of initial current and initial voltage in the energy storage elements in the circuit. Okay, let's introduce some terminology here. The characteristic equation is obtained by setting all of the independent sources to 0 and replacing the derivative by s and the second derivative by s squared. And for the natural response, it looks something like this for the parallel RLC circuit. The next terminology we will introduce are the characteristic roots, S1 and S2, and they're the solutions to this quadratic equation. They are expressed in terms of two other quantities, alpha, which is called the Neper frequency. It has units of radians per second, and that's just formed from R and C values. And omega naught, which is called the resonant radian frequency. That also has units of radians per second, but that just has L and C in it. In other words, the energy storage elements in the circuit. Now, this particular term is characteristic of the oscillations in the circuit, as we'll soon see. So the roots of the characteristic equation determine exactly what response the circuit will have. Looking at the values of the roots, they are the roots of a quadratic equation. There are two of them, and there's a square root involved. Let's look underneath the square root sign to see what happens for differing values of alpha and omega naught. The first case is when omega naught squared is less than alpha squared. In this case, the square root is a real number, and S1 and S2 are real and distinct. We say that Vt in this case is overdamped. That means the voltage approaches its final value without any oscillations whatsoever. It's kind of like a smooth curve. If we have the case where omega naught squared equals alpha squared, then S1 and S2 essentially converge and become real and equal. In this case, we call Vt being critically damped. This means that the voltage is sort of on the edge of oscillating about its final value, but it's just not quite oscillating. The third case, and this is the most interesting case, is what happens when omega naught squared is greater than alpha squared. In this case, the little bit underneath the square root there becomes negative, and therefore S1 and S2 become complex. Vt is therefore what we call underdamped. The voltage oscillates about its final value with oscillation frequency in radians per second equal to what's called the damped radian frequency, omega d. Omega d can be expressed as a function of omega naught and alpha, as shown here. Now, knowing that S1 and S2 are complex, if we pop them back into that general form of the solution for the differential equation, we'll find via Euler's identity that we will get oscillatory behaviour. We can express this equation in terms of cosine and j sine x. So we now know that the solution will have oscillatory behaviour to it. The oscillatory behaviour is dictated by several things. The Neper frequency, or alpha, as we've seen already, determines the rate of decay of the oscillations. It's also referred to as the damping factor. The resonant radian frequency, omega naught, is known as the natural frequency, and that determines the oscillation frequency if there was no damping present. And lastly, the damped radian frequency, or omega d, determines the oscillation frequency for the underdamped case. So we can imagine this system oscillating down eventually to its final value at a decaying rate that's governed by this Neper frequency alpha. Let's focus in on the first case, where omega naught squared is less than alpha squared. And we call that the overdamped case. In this case, S1 and S2, those characteristic roots, are real and distinct, and Vt is overdamped. So if we know S1 and S2, completing the description of the overdamped natural response means that we still have to find these two other constants, A1 and A2, as part of the general solution. These constants are determined by initial conditions, specifically from V, T, the voltage, and its derivative at time t equals 0. So if we just plug t equals 0 into this equation, we end up with one simple equation for A1 and A2. And if we differentiate this equation, which turns out to be really easy with respect to t, and then substitute in t equals 0, we end up with another equation for A1 and A2. Given two equations, two unknowns, we can easily solve for A1 and A2 to determine these constants. So let's summarise what we've just seen, the process for finding the overdamped response for a parallel RLC circuit. Step 1, find the values of alpha and omega naught and the characteristic roots S1 and S2 using our circuit parameters R, L and C. Step 2, find the value of V at t equals 0 and its derivative using any old circuit analysis technique that you like. Step 3, find the values of A1 and A2, those constants, by simultaneously solving the equations we just derived before and shown below. Step 4, substitute those values for S1, S2, A1 and A2 into our general form for the overdamped natural response solution, and this is valid for t greater than or equal to 0. As an example, let's look at the following parallel RLC circuit. There are two energy storage elements, an inductor that has some initial stored energy because it has an initial current in it of 30 milliamps, and a capacitor with an initial voltage of 12 volts across it. Now, if we go through the process and we solve for the characteristic roots, we solve for alpha and we solve for omega naught, we'll find that it's an overdamped circuit, but in particular it has the response for the voltage that has the following form. If we show this graphically, we'll see clearly that it exhibits no oscillations. So therefore, it's an overdamped natural response. Now, because there's a resistor in this circuit, eventually all of the stored energy will decay to 0, and therefore the voltage will decay to 0, as shown in the graph.